Hey math fans, welcome to section 2.2 of probability theory when we discuss the addition law for probabilities. So in this lesson, we're going to discuss the probabilities of unions of events, including ones that are mutually exclusive versus ones that are not mutually exclusive, as well as unions that are finite versus not finite. And then we're going to end off by proving the first Borel-Cantelli lemma. All right, let's get started. So first of all, the simplest kind of scenario is to let A1 and A2 be two mutually exclusive events. Mutually exclusive events of an experiment. And we're going to go ahead and define the event A as the simple union between A1 and A2. Okay, so since A1 and A2 are mutually exclusive, the event A just consists of either A1 or A2. There's no overlap. Okay, so we're going to go ahead and define n, little n, as the number of trials in the experiment. Number of trials in the experiment. And we're going to make a couple of definitions. This should remind you of stuff from chapter 1. So we're going to define, I guess I can do this all in a different color. So we're going to define n of A as the number of trials leading to the event A. We're going to define n of A1 as very similarly. We're going to just define that as the number of trials leading to A1. Okay, and logically, n of A2 is going to be, let's see if I can do this. Number of trials, the number of trials leading to A2. Leading to A2. Okay, so let's think about this for a second. We're just counting trials. That's all we're doing. So for any event A, there are two possibilities if A occurs. It either occurs by A1 or it occurs by A2. There's no overlap. So when you're counting these guys, we have a very, very simple relationship here, which is that clearly the number of trials where A occurs is simply the number of trials where A1 occurs plus the number of trials where A2 occurs. Technically, this is kind of an axiom of sorts. We are kind of assuming that this is true because everything we're going to discuss this section relies on this. So make sure it kind of makes sense. And from experimental results, this holds. Okay, so if this holds, this implies that I can divide every side by little n, and I get the experimental probabilities. And now let n approach infinity. So that means that the experimental probability is then going to approach the theoretical probability. See the videos in chapter 1 if you need a refresher on that. But if you take the limit as n approaches infinity, then these turn into probabilities, experimental probabilities. So we get that the probability of A equals the probability of A1 plus the probability of A2. And I'm going to go ahead and box this. This is the first so-called addition law. And it kind of makes sense, right? If you have two events that are mutually exclusive in some sample space, and you want the probability of A1 or A2, just add them up. No big deal. Right? Okay. Now, in general, for events A1, A2, all the way up to A sub k, assuming that they're also mutually exclusive, and we assume that the event A can be written as this union of all the A sub k's, then similarly, we of course have that the probability of A occurring is going to be the same as the probability of this union occurring. Then you can just simply apply this formula many times, and you get the result that this is going to be, the probability of A1 plus the probability of A2 plus all the way until the probability of M, if there are M of the events. Okay, so a more succinct way to write this is using the sum notation, the summation notation. So we're going to go ahead and say that this is equal to capital sigma. We're summing over the k's of the probability of each of the A sub k's. Okay. So from this, we can actually derive a really important theorem. And I'm going to go ahead and state it in only 2 parts. The book states it as 5 parts, but we're going to go and say theorem 2.1. And the assumption for this theorem is everything above. Okay. We're assuming actually that the events are not necessarily mutually exclusive, and we're essentially going to prove the following results. Number 1, the probability of A1 union A2 that's not necessarily mutually exclusive is going to equal the probability of A1 plus the probability of A2 minus the probability of their intersection. Okay, and the second one, if A1 is a subset of A2, that means that the probability of A1 is less than or equal to the probability of A2. All right, now this is really easy to see from a Venn diagram, so let me just show you the picture. So if there is overlap between the events A1 and A2, and I want the probability of A1 or A2, then the idea is that first you have to add the probability of A1, then you have to add the probability of A2. Okay, but then there's a problem because I just double counted the intersection. Okay, so I have to actually remove that just once. Okay, so it doesn't really matter which one holds, but you only have to remove the double intersection one time. And then you have the probability of A1 or A2 with that union. That's a pretty simple picture, but we're going to prove it, and it's actually going to take some effort. So let's go ahead and do that. Okay. Proof. Okay, so note that for A equals A1 union A2, with A1, A2 not necessarily mutually exclusive. I guess it could be, but we're not assuming that. We have the following results. The event A1 can occur one of 2 ways. Either A1 is in A1 and A2, or it's an A1 and not A2. So either A1 is actually in the intersection or it's its own thing. So the way we can say that is A1 is either in A1 minus A2, or it's an A1 intersect A2. Those are the only 2 possibilities. Okay, so think about that for a second. Okay, so likewise, we have that A2 is either in A2 and not A1, or it's in A2 and A1. Okay, but A2 and A1 is the same really as A1 intersect A2. So I'm just going to go ahead and flip that. Okay, and the important part is that these events, while A1 and A2 aren't necessarily mutually exclusive, A1 and not A2, as well as A1 and A2, are mutually exclusive. You are either in A1 and not A2, or you're in A1 and A2. Okay, so since everything's mutually exclusive here, now we can use the first result. Okay, so this essentially implies that the probability of A1 is equal to the probability of this plus the probability of that. Since they're mutually exclusive, we can go ahead and use that result. So we have that the probability of A1 is equal to the probability of A1 and not A2 plus the probability of A1 intersect A2. And we also have, likewise, the probability of A2 is equal to the probability of A2 and not A1 plus the probability of their intersection. Okay. Now let's talk about what the event A1 union A2 actually means. We're going to talk about kind of what this is, because we want a formula for the probability of A. Okay. So let's think about this for a second. The event A1 union A2 can occur in one of three ways. If you are either in A1 or A2, that means that you are either in the set difference A1 minus A2, or you're in the set difference A2 minus A1, or you're in the intersection. Okay, so really quickly, let me just kind of describe what this means. This is saying you are in A1 only, or you're in A2 only, or you're in both A1 and A2. Because this means at least you're in at least one of them. Well, that's either 1 or 2. So these possibilities are the 1, and this one is the 2. Okay. Okay, so now let's take the probability of this, and let's see if we can connect some dots. Okay, so this implies that the probability of A, which is the same as the probability of A1 union A2, is equal to the probability of A1 and not A2 plus the probability of A2 and not A1 plus the probability of the intersection A1 and A2. Okay. So let's see if we can mess around with some of this. So the thing that I want to mess around with is this part of the formula. Because it's really difficult to figure out what the probability of A1 and not A2 is. So we're going to see if we can substitute that in. Let's go up here and see if we can figure that out. Okay, so I'm going to try to do this in maybe red. We're going to use this stuff. Is there a way that we can get the probability of A1 minus A2 plus the probability of A2 minus A1? Well, yeah. Just take both of these equations and just add them together. Okay? So I'm going to denote this, well, I think a better way to do it would just be to copy that. Let's go down and mess with it. All right, so since we have this result, it follows that we can just add the equations together and get that the probability of A1 plus the probability of A2 is equal to the probability of A1 minus A2 plus the probability of A2 minus A1, plus we have 2 of these, so keep that in mind, plus 2 times the probability of A1 intersect A2. Okay, we're getting there. We're actually pretty close. Now, I'm going to go and highlight that portion again because it's the same thing. And if you solve for this quantity right here, you just have to move this over and this over to the other side. Okay, so if you do that, you can make the substitution that this probability is this probability minus this minus that. Okay, so really this is going to be equivalent to saying that the probability of A1 plus the probability of A2 is equal to, and I'm going to make that substitution, it's going to be the probability of A minus the probability of A1 union A2 minus the probability of A1 intersect A2 plus 2 times the probability of A1 intersect A2. Okay, so really these are the same thing. So yeah. So this is just simply probability of A. Okay, there we go. So now we have 2 like terms. We have this one and this one. A negative probability of A1 intersect A2 plus 2 probabilities of A1 intersect A2. Well, one of them is going to win. Okay, so we get probability of A1 plus probability of A2 equal to the probability of A plus the probability of A1 intersect A2. And finally, to get the probability of this complex event A by itself, we're going to go ahead and subtract this over. Okay, so we get that the probability of A is exactly as desired. Probability of A1 plus the probability of A2 minus the probability of their intersection. Okay. Now, this was the proof of number 1. We still have to prove the number 2, which says if A1 is a subset of A2, then the probability of A1 is less than or equal to the probability of A2. So let's go ahead and do that. It's not going to be as long, trust me. Okay. Okay, so quickly a picture. I mean, if A1 is entirely within A2, then it makes sense that this probability is going to be less than or equal to this overall probability. Okay, but let's go ahead and just show that. Okay. On the other hand, the probability of A1 is the probability of A1 intersect A2. If you look at it, the event A1 shaded in orange right here, whoops, meant to shade that, is nothing other, since A1 is entirely within A2, if we're including A1 and A2, that just has to be A1. Okay. So what does this equal? Well, how do we get A1 and A2? Well, let's start off with A2. A2 covers everything. Okay, so I have to then subtract off the part that is just A2 without A1. All right. But this has to be less than or equal to, because this probability has to be between 0 and 1. It is a positive number that you are subtracting from the probability of A2. So you are actually decreasing it, which means it has to be less than or equal to the probability of A2. Okay, so that essentially proves the claim. And this proves the theorem. Okay, I want to end off this example with, I want to end off this video with an example that's actually taken from the Society of Actuaries exam, just to show you how some of these relations hold. All right, so let's work through this example as the last thing we do in this video. This is from the Society of Actuaries problem number 3, and it says that given that the probability of the union of A and B is 0.7, and the probability of the union of A and B complement is 0.9, find the probability of A. So there are going to be two ways of doing this. So I'm going to show you kind of the way that is based off of stuff we learned in this video. So we'll call this solution number 1. Okay, so the first thing to consider is that the probability of A union B is the same as the probability of A plus the probability of B minus the probability of A intersect B. This is the same exact formula, but instead of A1 and A2, I just replace them with A and B. The next thing that we know is the probability of A union B complement is the same thing. It's the probability of the first event plus the probability of the second event minus the probability of the first event intersected with the second event. Okay, now we have a couple of substitutions that we can make. The first one is dealing with the probability of A. Okay, remember that the probability of A is actually going to be the same thing as the probability of A intersect B minus the probability of, okay, I got that wrong. Sorry, the probability of A is equal to the probability of A and not B plus the probability of A intersect B. Okay, so just think about a situation in which you have A and B, and then this probability of A is the probability of A and not B plus this intersection. Okay, so I'm going to go ahead and substitute that in. So we have that probability of A union B is equal to probability of A not B plus the probability of the intersection of A and B. Okay, and of course I have the rest plus the probability of B minus the probability of A intersect B. Okay, so if I call this equation 1, call this equation 2, we might call this equation 1 prime. Now, the important part here is that the probability of A intersect B cancels, which is good because I don't know the probability of A intersect B. Okay, and then the second equation, if I were to adjust it, I'm only going to make one substitution here, and that's going to be this term. Because the probability of A intersect B complement is really the same thing as the probability of A and not B, which is the same as the set difference. It's the same as the set difference A and not B, right? They're really the same thing. You can watch the video on 2.1 for a verification of this. And we can go ahead and substitute that in. Okay, so we get that this is 2 prime, the probability of A union B complement is equal to probability of A plus the probability of B complement minus, now I'm going to substitute in probability of A minus B. Now the only thing that I have left to do is add these 2 equations together. That wasn't very straight. Okay, there we go. All right, so if I add these 2 equations together, a couple of nice things happen. When I add the 2 equations together, the set differences just cancel, and I'm left with the probability of A union B, which we're given, plus the probability of A union B complement, which we're also given, is equal to the probability of A plus the probability of B complement. Okay, and I don't know why I just highlighted those. Probability of A plus the probability of B plus the probability of B complement all right, and that's it. Now, the probability of B plus the probability of B complement, let's think about that for a second. There are only 2 possibilities. Either you're in B or you're in B complement. Since they're the only 2 possibilities and they're mutually exclusive, those probabilities, by a quick application of Theorem 2.1, or whichever was the first one in this video, this is 1. Those probabilities have to add up to 1. They make up the entire sample space. Okay, so I can now substitute in the values, and let's see if we can figure this out. So I have 0.7 plus 0.9 is equal to the probability of A, which I'm trying to find, plus 1. And then from here, we get the answer that the probability of A is 0.6. That's the first solution. And I'm going to have to be honest with you. All of this is beautiful and elegant, and it really ties together everything we talked about in this video. This is not the way that I would approach the problem in the actuarial exam. Okay, exam P, you ain't got time for that. So let me show you another way that relies on pictures. So this is solution number 2. Okay. So let me just rewrite the 2 facts for us really quickly. So we have the probability of A or B is 0.7. And we have the probability of A not B is 0.9. Okay, I would just draw a big old picture where this is event A, this is event B, the entire sample space adds up to 1 basically. So if you want to put that down, it's fine. Okay, so this is A and this is B. Let's see if we can't write some stuff down. Okay. So we have that A or B is 0.7. So if you're either in A or in B, that's 0.7, which means everything else in the sample space has to be the rest of 1. Okay, so everything else has to add up to 0.3 if these 2 circles combined have to add up to 0.7. Okay, the next thing that I can say is that the probability of A or B complement is 0.9. So recall that by De Morgan's laws, the complement of this is equal to A complement intersect B complement complement, which is equal to A complement intersect B. Okay, well, what is A complement intersect with B? Well, that's nothing other than the set difference. And that set difference is going to be this region. Okay, so if the probability of A or B complement, if this is 0.9, then the probability of the complement of that has to be 0.1 because they have to add up to 1, which means this value is 0.1. And if you add everything together, everything has to add up to 1. So this plus this plus this equals 0.1. So from there, you can conclude that the entire circle A has to have probability of 0.6. So if I were on the actuarial exam, I would rely solely on Venn diagrams and pictures in order to answer the question in the least amount of time possible, because there's no guarantee that you're going to get the correct answer even doing all of this theory, and you're going to have to substitute and it might take some time. Okay, so hope that was helpful, and I'll see you in the next video.